Okay, so good morning. So first I owe you some numerics from yesterday because just to illustrate the non-self-averaging property of the spectral form factor. So this is some old numerics from one of our papers, but you find such plots in the literature, also in the, let's say, single particle problems in 80s and 90s. So this is for the, actually, it is for the clean version. I mean, that clean means that there is no disorder, but it is for the version of the model that I'm going to discuss today, the decreasing chain. And the black plots that you see on this graph is actually numerical data that you get if you compute the spectral form factor, right? I mean, just to remind you what we are computing. So. Okay, then we subtract the delta at time equal to 0, but doesn't matter so much. But now, if you don't do any averaging, this is what you get, these black points, yeah? And here, in this particular case, we don't do any other averages. I mean, then you have these nice full curves here. I mean, the red curve actually is a random matrix result, but the black curve is numerics. And that black curve, which is kind of nicely following random matrix result, which is behind the red one, you get simply by moving time averages over 100 bins of this data. Yeah? So that's just to show that even moving time average is enough. So we don't have to have very fancy ensemble averages in practice. But still, we would like to do some sort of averages over an ensemble of models here. Okay, so now, since yesterday I did much less than I hoped for the first lecture, I will now continue on this first model from slides. And then I will switch on the board when we go to the second model, which is kind of probably more important to discuss. But the first model was simply to give you some heuristic ideas how we can handle this type of problems. Sorry. That should.
Sorry, the window is how big on this scale?
The window, you mean?
Yeah, the window over which you average?
It's 100 points, 100 times. 100. So time is discrete. This is a kick system, so time is measured in number of kicks. I think this is a system of size 18 or something, so it's a, but then it has a translation invariance. Because it's clean, it has translation invariance, so you separate the momentum blocks. So it's 2 to the 18 over 18, roughly, the Hilbert space. Okay. So it's still big, to 10,000. Then you divide in bins of 100, and then you average over, I mean, moving time average, or windows of time. Okay, so now, right, so now this is the model that I introduced yesterday. I mean, this is a reference that you can find more details about this. So basically, it's a Ising model where you have arbitrary long-range Ising interaction, possibly long-range Ising interactions for the diagonal part, and then you have the off-diagonal part, which is transverse field. You write time ordered exponential, which is just the product of V's and W's. Maybe I used some different sign and order conventions yesterday on the board. Doesn't matter so much. Then what we arrived to yesterday was this lengthy formula, which is not so horrible as it looks, because we now want to average over the phases, right? So now phases are the eigenphases of this diagonal part of the propagator, and then the off-diagonal parts also are very simple. They are factorizing to a product of this one particle perturbation, one particle matrix, which I call little v, which are just two elements, these two elements, cosine h or I sine h. Yeah? And then, as I said already yesterday, we assume pseudo-randomness of phases, which means that we can, I mean, that's the assumption, right? And that assumption makes this as a kind of a random model again. I mean, it's a random phase model, right? But then, of course, there are maybe corrections to that for particular dynamic consistence, which I would, argue that there are simply small fluctuations. Yeah? And then we will check by comparing to some practical, let's say, long-range Ising models and see how it works. Yeah. So, but let's see what this assumption implies us, because sure.
Yeah. So you want to assume pseudo-randomness. Now, one of the covenants of the model, say J1 X, right, is actually purely random, right?
Right.
Is this going to be enough to guarantee pseudo-randomness?
Well, I mean, well, if you say if one of them is.
Yes.
Well, that's more, well, I mean, depends how many you have them. I mean, for example, if you have, there are these parameters, right? So my kind of wish is that, you don't need any randomness, but just enough parameters, right? right? It's like you have this pseudo disorder, right? I mean, but you need enough parameters, right? A pseudo disorder is not really disorder, but if you add, for example, sufficiently nonlinear functions of this.
That's gonna be. I was thinking, however, if you get rid of all multiple interactions, it's just the J1 term, then you actually should not see that, right?
No, of course not. Yeah,
So
because you need coupling.
In J1, it's not gonna be.
No, of course not. I mean, we made this simple calculation yesterday with just this term, right? And this goes. And I think that you need at least these two terms. But I will show you that there's enough to have two body interactions plus one body term if two body interactions are long ranged. Yeah. But again, I tried yesterday. Someone asked me. I mean, short range two body interactions are not enough because they don't give extensive interaction energy of a single spin. I mean, but. Okay, I mean, again, this is heuristics, yeah, so we can spend many words, but still things are not clear. So it's better to do numerics and see how it works, but then let's go to the next step where we can do some analytics, yeah. But still, I mean, I think it's useful because the main point here is, again, I want to remind you what is the main point. The main point is to explain the linear ramp, right? I mean, that's the level correlations. I mean, again, I will just maybe put here a small diagram, which I already plotted yesterday. What we should expect for different type of models. So this is the Heisenberg time. And now for let's say unitary ensemble of random matrices, you get something like this. Then for random spectra, which are supposed to be valid for integrable systems, you get Poisson. So this is CUE, and then we get also, for example, COE, like this. But you see from here to here, there is exponential gap. So you have a kind of experiment which can measure k of t for small t. That's super sensitive to chaos. That's level compressibility, basically. And this is exponential. For a many body system, this is exponential gap. It's really, I mean, this is what I want to advocate here, right? So we want to understand why we have this ramp here. That's the point of my two lectures here. So I hope I can convey this simple, I mean, one of these simple ideas how to explain this. Okay. So, I mean, now let's look at this horrible sum, right? Now, using this, then, of course, you see, I mean, this double sum over this. This is like path integral. It's like a double path integral over two, let's say, forward and backward paths. But now this basically gives us some constraint that this forward path should be basically a permutation of the backward path, yeah? And that's, that's the idea. So, so once you have this, I mean, again, I explained this. This is just a sequence of an ordered, lexicographically ordered sequence of spin configurations should be equal to this lexicographically ordered sequence of spin configurations. So it means if these guys don't repeat, that this should be permutation of that. And now let's assume that for times much less than the Heisenberg time, this will never repeat because there is 2 to the L permutations, 2 to the L spin configurations. So by chance, I mean, probability of repetition will be 1 over 2 to the L. So this will almost never happen for times much less than 2 to the L. Of course, when you start approaching Heisenberg time, this will start happening. And that's exactly where you get next order corrections to the linear ramp. So one can actually repeat this step. One can do the next step. For example, one can get Sieber-Richter type pairs, for those who know. I mean, there is the next type of orbits. I mean, basically, we are now going into the kind of ideas which are similar to periodic orbit theory, even though there is no semi-classic. So far, I would now like to isolate the Barry's term, the term which comes from simple, I mean, if you want, diagonal approximation. Yeah. Again, these buzzwords are only for those who know the buzzwords. So, I mean, otherwise, it's just combinatorics for us. So what do we do? And again, I mean, I apologize for going too fast here, but probably too fast. I just want to give the main idea because then I want to go to the next example, where I again go slower and try to get more into detail. So, but now, I mean, you see, once you kind of accept this idea, then basically this horrible sum now becomes a very simple thing, right? Because now you say, okay, the primed configuration should be a permutation of unprimed configuration. So basically, only sum over unprimed times a sum over permutations, yeah? Where primes are permutations of the unprimed. But then this sum over space now goes into the product, right? I mean, this is simply a multiple sum over L copies, but this is just an Lth power, right? So that you get this nice formula. Basically, you get that spectral form factor is a sum over permutation group of T elements. This is an approximation now, approximation for short times, because you assume that there's no repetitions, but for short times is an excellent approximation. And then each term in this expansion, which depends on the permutation, is looking like an Ising model partition function. 1D Ising model partition function. We call this a twisted Ising model because for non-trivial permutation, you get these weights, which are permutations of these weights. So this is not positive weights for non-trivial permutations. However, now you can ask, because this is now to power L. Now let's go to the large system size limit. If you go to large system size, then of course the dominant term here are those, then if one of these partition functions is by gap larger than all the others, then this will give you, in thermodynamic limit, exponentially dominant term. And it is possible to argue that there is the largest one, which is given simply by the identity, or all the symmetries of the partition function of the Ising model. So the identity permutation basically gives you the positive weights here and gives you the simple Ising model partition function. But there is not only identity, there is actually two T such partition, two T such permutations which are given by the permutations which conserve the neighbors. What happens now, this only depends on which two spins are neighbors. So then you have basically a partition function on a ring, right? Which has two T sides. Now basically this transforms to stat mech in time, right? The space now, the configuration space now is time. So you have T spins. And now, and then you have two copies basically. And now you want that partition, now you want that you have such a permutation which conserves, which maps two neighbors to two neighbors. Right? Any such permutation which will conserve this partition function. And there is, of course, this is simple kind of theory of discrete groups. There is, of course, a group which conserves this type of things. This is the dihedral group. This is just cyclic permutations times reflection. So there's two T such elements, yeah? It's exactly that. So you can show that any other permutation will scramble at least one of the pair of neighbors, and it will produce a gap in this partition function. Okay, is this more or less clear? That's, I didn't want to go deeper here because it's a very simple combinatorics, yeah? So then what you get is basically 2T times a trace of the transfer matrix of a 1D Ising partition function, right? So it's 2T, that's already the ramp, you see? The ramp is simply a symmetry in time. It's a rotational symmetry in time, times reflection, which is time reversal. So it's 2T. So this model is time reversal symmetric, so it has 2T ramp, yeah? It's of this type. But now you get also corrections to that. Of course, now I didn't discuss yet this time scale, but it's often of interest to discuss a time scale which is sometimes referred to as the tau-less time. This time is defined such that for times less than tau-less, or sometimes it's referred to as Ehrenfest time, depends on the context and community, but this is a time which designates a transition between random matrix behavior and non-universal behavior. It turns out that for very short times, you might not expect random matrix theory to be valid for describing spectral form factor. For example, in semi-classical models, very short time is described by simply classical mechanics. So periodic orbits, for example, will kind of make deviations from this. So now we have explicit formula. This formula should supposed to be valid for any time, but you see, for short times, basically you have transfer matrix of a 1D Ising model, which is this one, to power L. Now this is the kind of 5-minute exercise, which I will not do now, but which you can do, and which simply gives you this result. And this result tells you, okay, this is nice if 2H, now you see, okay, I'm sorry, and now I didn't realize that in my slides I use different parameter, different relator for transverse field, but this H is the transverse field, yeah? This H was a transverse field. Now, in my Blackboard talk yesterday was B, because H I want reserved for this one. But anyway, that's the transverse field. So you see, this is the only parameter which remains in this solution. So this is a one-parameter family of solutions, and that's the key parameter, right? Because if you don't kick the model, if H is 0, then basically you get here 2, and this is 2 to the L, and 2 to the L is Poisson. So basically you get form factor of the order of 2 to the L, which is no level correlations, yeah? But now if this H is smaller than L, smaller than, if H is different from 0, if 2H is different from 0 or 2 pi, so if H is different from 0 or pi or 2, you also don't want it to be -1, But anyway, if this is in magnitude less than 1, so this will now be exponentially decaying in time, which means that there will be a time which you can simply determine by, again, elementary analysis, T star, which is log L over log cosine 2h, such that this will be very well approximated by 2t, asymptotically. So this is the expression for the tau star. Now I will still use 2b. Okay, so now there's this interesting, intriguing log n, which is occurring in different contexts. People have found something like that in different models. For example, there was an interesting related study of the group of John Chocker, Andrea De Luca, and Chan, where they have looked at random quantum circuits, local quantum circuits with large local Hilbert space dimension. And they found exactly the same scaling of the tau time, even though the context was completely different. I mean, there they had local interactions, but they used a regime in which local Hilbert space dimension was not 2, but was a large number. And then again, they got this log n scaling of the tau time. So it seems to be kind of ubiquitous. I mean, it's emerging in many ways. Yeah. Okay, so now. Let me just, okay, so then there are corrections. I mean, you can discuss now corrections to this. You can discuss the contributions of subdominant twisted partition functions. And you can see that these contributions can be ordered in terms of some sort of diagrams. So the subleading diagrams are actually those permutations which actually scramble just one neighbor. We call them single X diagram. And for that single X diagram, you can calculate explicitly the contribution to this partition function. And you see that they are basically gapped. Yeah? For b, which is not equal to 0 or pi over 2, these are gapped. So they give us exponentially small contributions. And then one can also derive the second order corrections in time, which is exactly this Sieber-Richter corrections to spectral form factor of random matrix theory. So basically you just now classify your sequences into such which have no repetitions, and then such which have exactly one repetition, which would be corresponding to this shape 8 orbits, and so on and so forth. Now, this is kind of pure combinatoric version of, let's say, if you want periodic orbit expansion. Okay, now let's just, before I close this example and go to the next chapter, let me just check now, I mean, show you how it works. I mean, because now still we haven't seen that this actually works. So now let's just, I mean, again, this I already introduced yesterday. I mean, we kind of consider now this simple long-range Ising model. Now, again, I call it clean because there is no disorder. Now, I apologize for notation. Now, by x, I denote position on the lattice, which is the integer. So now this is alpha. The key parameters here are j, b, maybe a. I don't know. I don't think it's not crucial, and power alpha. And then there are these Katz normalizations, which enforce the overall energy to be extensive. And then we thought at that point that maybe it would be useful for example, to compute, to show not the form factor itself, but the integrated form factor, which is self-averaging for long times. As you have seen, if you do moving time averages, then form factor becomes self-averaging for large windows of time. So by the same reasoning, this guy will become self-averaging in the limit of large times. Yeah. So this is basically if k of t goes like t, then integrated k of t goes like t squared, and for Poisson you would expect to go like t. Okay. So now it's just to have results which are more crisp, but still, I mean, I think, I will show you later also some plot of the crude, I mean, the raw spectral form factor. So this is the integrated spectral form factor. These are data for different models. So this is H transverse field. 0 means Poisson, that means just Ising model, and then these are kicks, yeah, the transverse field kicks. And the pi over 4 is the value where the kick is maximal. Basically at pi over 4, and remember this value pi over 4, it will turn out to be important later. For pi over 4, this contribution is 0. So the tauless time basically is this is 0, so log 0. Yeah. The tauless time is basically 0 because then this log 0 becomes minus infinity, so this goes to 0, right? So basically it means there is no effect, basically the form factor is 2t from the scratch, right? From t equal 1. Okay, so now this is the maximal disorder. You see, I mean, here the theory would give you just flat line, which is integrated t, which is t squared over 2. And now for other values of transverse field, you will get some non-universal effects. Then you get asymptotic linear ramp, and then you will get, then here the Heisenberg time is, I think, around here. Then you get bending to slope 1. Yeah. So slope 2 is the linear ramp of random matrix theory. And you see that I have excellent agreement between the actual model. I mean, this is a model, I think, with no averaging. And then, or maybe there is, I mean, forgot, maybe there is an averaging over 10 samples, I think 10 different values of parameters, J. And here, we just plot all these 10 values, right? These different, this is just an inset, just a magnification of this small time part. And these different curves here are different values of the system parameter, and then this orange one is the average. Yeah. So here, I mean, I'm more specific here. We take average over 10 J realizations. So 10 different values of the. No, we are averaging the quantity. Yeah. Yeah, but yeah, right. Right. It's because yeah. Sorry. Right. But you see, the average is on the upper level. Yeah. So it's the averaging the quantity itself. Yeah. But yeah, okay. Now here is just to convince you that maybe this averaging is not so crucial. I mean, now here we plot it in again. Okay, here the time scale is normal, but this scale is still log. The theory is black, and then the two noisy curves are, I mean, again, which are kind of within expected fluctuation, which we are fluctuating around the theory. One of them is moving time average over 10 consecutive time steps, and the other is average over 10 J realizations. Yeah, basically they are fluctuating around the same. I mean, just to make sure that basically the things make sense. Yeah. Okay, so now, right, and now this is to show you that this range of alpha is kind of, you see, I mean, this is just an empirical check when this model works. So we sort of devise some sort of benchmark of quality of this description, right? I mean, I think this is some sort of difference between numerical and random matrix form factor integrated over all times, scaled such that 1 would be like excellent agreement. And right, and so you see, I mean, basically for alphas between 1 and 2 things are excellent, yeah? And then basically they start to, this is mean field and this is short range. Yeah? Okay, so now this was some numerics, yeah? Now I will, can I now switch off this? I mean, to remove the screen, please. Okay, so now let's now discuss what happens with models with short range interactions. So you see, I mean, what these long range interactions, why is this long range model much simpler? I mean, the reason is that, of course, I mean, you see, when we map this long range model, we map the problem of calculating spectral form factor for long range model to StatMech in 1D, basically. I mean, of course, we organize it to many layers. I mean, there was this sum over partition over permutation group, but still, each term was like a partition function of a 1D StatMech model. Now, if you have short-range interactions, you can't do that. And basically, for short-range models, you will see that basically this problem maps to StatMech in 2D. So now let's see how this goes. And that StatMech is not actually standard StatMech because, you know, there are partition functions with non-positive weights, with complex weights. So you have to be able to say something about models, kind of vertex-like models with partition functions which are not non-positive. Yeah. So now, but still, I mean, and here basically one has to use some sort of, one has to use unitarity, yeah? And I will show you how. I mean, these are now just a few buzzwords, but I will try to explain how this goes. Okay, so now, so locally interacting. ICTS model. So I will now define again a Hamiltonian which will be depending now on two sets of parameters. I'll try to make it as precise as I can. So there will be again an easing part, but now easing part will depend explicitly. I will now study explicitly its dependence on a string of field parameters. So there is parameter J, which is kind of a global parameter, and then there are these local field parameters, Hj, sigma j. So Hj is a longitudinal field. And then, of course, I use periodic boundary conditions. And then I will use kick, which is again depending on a single parameter, which I will call B. And the field will be a vector of L real numbers. And this will be my ensemble now, right? My ensemble of models will be specified by specifying this, the set of a vector of the fields, yeah? So, I mean, I will try to average, I mean, then there'll be, I mean, I will then average over disorder. I mean, now I have to, I want to produce some exact results, so I have to do some averaging. But at the end of the day, you will see that this averaging can be arbitrarily small. So there will be some ball in space of disorders, but this ball I will shrink to a point at the end. But that will be at the end. So there will be always some disorder which will kind of be important, yeah. And so what we want to calculate now, we want to calculate again. So now, okay, first. And then of course what is this delta P is a periodic delta, right? So what we want to calculate now let's define again the kick-teasing Floquet operator, one propagator or one period of the evolution, yeah? So that's 2 to the L by 2 to the L matrix in this standard space. I mean, let's say in the sigma z eigenbasis, which will be the computational basis for us again. And now what we want to do is we want to calculate first k of t, which will be trace of u kick-teasing. Now, k of t, of course, here depends explicitly on the parameters of the model. And then in the next step, so this will be first step, and the next step will be we'll calculate k bar of t, which will be some expectation value of this guy, average with respect to the vector of the fields, with some specified distribution. So I basically, what I will do, we will just assume that these Hj are IID variables with some distribution. We'll take Gaussian, but it turns out that it's not important which distribution you want. Okay, so now, first step. So now let's just write the trace of, so for the first kind of the same as in the previous example. Okay, sorry, here we need power t. So now let's write, so this superscript means a power, right? U to power t. So now let's write first the trace of the t power of the propagator, again, as in a kind of path integral fashion. So I mean, I do the same as before. I insert t identities. So basically, again, I have here multiple summations over t. So s tau running from 1 to t. And each s tau is a string of L integers, sorry, signs, plus minus 1, classical spin values. And then, right, and then you can, again, take note that this is, of course, an eigenstate of this guy, and this guy just acts as a product, as a tensor product. I mean, it basically checks a matrix element between each component of this guy and this guy, right? I mean, it's the same thing. I mean, I won't repeat, but I just remind you of my yesterday's lecture. I mean, I spelled out explicitly how the matrix elements of these two terms look like. Now, this is just a special case. This model, in this sense, is just a special case of the model that I had yesterday. So I can immediately write the partition function. I mean, the expression for this, and then we will discuss it. Yeah. So this is a product over. Maybe I forgot also the product sign here, right? Here, product here. Right, there are the terms here. So now each term is still a product over spatial index j from 1 to L. Now this is V S sub tau comma j, S tau plus 1 comma j, and then e to the minus I sum over j. Again, 1 to L, j, s, j, comma tau, sorry, tau, comma j, s, tau, comma j plus 1, plus hj, s, tau, j. Okay. And now, remember what it is. This guy, I will just remind you, v plus plus is v minus minus is cosine b, and v plus minus is v minus plus, minus I sine b, right? So this is exponential of e to the minus I b sigma x, right? This matrix has two elements, one on diagonal, one off diagonal. These two elements, yeah? So here, okay? Now, good. Right, and I remind you again, I mean, this, if you call this S tau, this is S tau, comma j. Okay, so now what I can do now is take the logarithm, I mean, take this as an exponential of the logarithm of that, so then this becomes exponential of the sum of those guys, and this can be added into this cost function in the exponential, right? And of course, if you do this carefully, and I mean, probably it looks obvious, but just I don't want to spend too much time on details. So if you do this carefully, what you get is basically this type of expression. There's an overall prefactor, which you don't want to put into the exponential, but it's kind of normalization, if you want. Sorry, and there is sum over S tau j. So now this is sum over these spin configurations, but now I call them like a partition function over 2D classical spin model, which spins S tau comma j, tau running from 1 to T, j running from 1 to L. And now this is e to the minus I, some energy function which depends on spin configuration on this rectangular array and the vector of the fields. And then I spell out also this spin, this energy function. Start with this term, and then I write another term with another coupling parameter j tilde, S tau j, S tau plus 1 j. So this is coupling in space, this is coupling in time direction, and then there is external field, which depends on space coordinate. So this looks like a 2D Ising model. It's like a partition function of 2D Ising model. And now let's kind of sketch it, sketch this Now this would be time for us. In this example, this would be space. So this goes from 1, and now here is the field. Let's say here we indicate a field, H1, H2 to HL. And this is time, so going from 1 to T. And then there are periodic boundary conditions in both. Okay, and right, so so now you assume that classical spins live on vertices of this L by T lattice. And what we have now represented is a spectral form factor, not yet spectral form factor, just a trace of the propagator for time t as a partition function, as a complex weight partition function of a classical spin model, which has field, and where field depends explicitly on position. Exactly, J tilde comes from the B term, right? And I will spell out what J tilde is. I mean, that's again a kind of very elementary. I mean, just take the logarithm of that, whatever. Just take out the overall normalization factor, and what is left is expression for J tilde, which is minus pi over 4, which comes from this minus I in front, and then there is minus I over 2 times log tangent of B. Okay, so now now the question is what you can do. I mean, of course, you cannot do much because this is not an integrable model. You're not. I mean, don't know even. I mean, if you complexify the weights, I mean, maybe without this term you would calculate this because this is known to be integrable. But but with field, I mean, we have no explicit solution for this partition function. But now we don't really want to compute that. What we want to compute is an average over the fields. Yeah. And we don't want to compute average of the over the fields of this guy, but we want to compute the average of this guy times its complex conjugate, right? Okay, so now, and this I argue this can be done, right? So, and first, before try to enter this calculation, I mean, again, now the question is how do I average over the fields? And I mean, the main kind of trick of this method will be kind of to show you how to average over the fields, how to compute some sort of how to define a transfer matrix which incorporates these averages and gives you the form factor in terms of the eigenvalues and eigenvectors of that transfer matrix. And then, moreover, we will be able to classify it, I mean, to say a lot about the spectrum of that transfer matrix, right? So now, what are we doing? I mean, again, we are now calculating this partition function, but this partition function we have formulated already as a transfer matrix, I mean, in terms of a transfer matrix, which is contracting it in time, right? I mean, for example, we basically do this, right? Sorry, this is what we have denoted as U, right? U is like a transfer matrix, it's a column transfer matrix, which basically computes this partition function, right? But then we can also define a rectangular an orthogonal transfer matrix, which will be a row transfer matrix, which will do the same trick. So then this will denote as U tilde. And it happens that if you look at this expression, then basically this expression is quite symmetric with respect to space and time. I mean, you can flip the indices, space and time indices, and it looks the same. You also have to flip the J and the J tilde, and it looks the same, right? The only thing that changes now is that disorder no longer becomes disorder, and disorder now becomes clean but noisy, right? Because it changes from time to time, but it is the same for all points. Yeah? So now what I will do now, I introduce this row transfer matrix. And from the construction of this problem, I mean, if this transfer matrix is depending on 2 parameters and the field, this transfer matrix will be actually the same, but it will depend on different parameters. And the field this will depend on particular spatial coordinate J, and the field will be Hj times epsilon, where epsilon will be just my notation for a unit vector of identities. The identities, right? So that's something that we have to understand, right? Just from the symmetry of the problem, this is exactly the same transform. Algebraically has the same structure. I mean, it has different dimension. This is 2 to the L by 2 to the L. This is 2 to the T by 2 to the T. It acts on the, again, on the time Hilbert space, on a Hilbert space of T qubits, right? I mean, that's super elementary. Just look at the way this partition function, I mean, this energy is written. I mean, and now, of course, I can, now you see, I mean, there exists, and from this is obvious that there exists a function which maps these two parameters, J and B, to two other parameters, J tilde and B tilde. One part of this function I spelled out here. The other piece of this function is given, again, by symmetry. Oops. Right? So the other piece of this function is given by symmetry. You just replace tilde with non-tilde. So you can write the J is minus pi over 4 minus I over 2 log tanh B tilde. So that gives you this function. And now you can ask, okay, good, this function is some complex function. So you take real parameters J and B and you get complex, in general, complex parameter J tilde B tilde, which means that in general, U is unitary, but U tilde is non-unitary. However, I mean, why do I want to discuss unitarity of U tilde? I mean, it's because that I can already, I mean, I see from this expression, of course, a simple, what I call duality formula. I can write now trace of UKI to power T, right? Which depends on a set of disorder parameters. I can write it as a trace of a product. J goes from 1 to L, U tilde, UKI of HJ epsilon, right? So now that's just a contraction in time, and this is contraction in space of the same partition function, yeah? So you see, and the structure of this algebraic structure of this transfer matrix is exactly the same, but the problem is that this guy has in general complex parameters, right? This one has real parameters in the exponent, so it's unitary. This one has complex parameters in the exponent, is not unitary in general, right? Okay, so now, yeah, what part you want me to explain? Well, I mean, it's just, you know, one left side of the equation is just iterating powers in this direction. This is the same transfer matrix T times and then doing the trace. Sorry, I have to, yeah, and then doing the trace. Yeah? And this guy is multiplying spatial transfer matrices, which depends on magnetic fields, right? So that's why it's a product, it's not a power, because it's a different field, a different side. And then doing the trace. Yeah? Okay? So you see, I mean, okay. I think it should not be too strange to see that, no? I mean, the important thing is now we have to take care of the space, I mean, of the disorder, right? So which means that at each layer, I mean, there is this striped field, right? I mean, field is constant in, it's a static but disordered field, right? So it's constant in time, but varies in space. When we turn these things around, it is homogeneous but varies from transfer matrix to transfer matrix, right? But that's actually nice because you see, I mean, now what I want to do now, okay, first of all, I'll stress at this point already that the only thing that we can study in this business is, of course, unitary evolution, right? I mean, now this defines some sort of non-unitary evolution, which is strange. Maybe we can do this. I mean, this would be kind of very interesting to do. I mean, this for general parameters, but what we can do at the moment is the case in which U tilde is unitary as well. So these are the points. I mean, now when is U tilde also unitary? You can study this question quite systematically. I can establish precise conditions for that. These are points where J is equal to plus minus pi over 4 and B is equal to plus minus pi over 4. This means that also J tilde is plus minus pi over 4, and B tilde is plus minus pi over 4. Some combination of pluses and minuses. I will not specify the details here. It's an elementary problem. But in one of these 4 points, in either of these 4 points, you get that also the tilde parameters are real, which means that both are unitary. We call these points self-dual points. Self-dual cases. I mean, it's a bit of abuse of the word. I mean, by self-dual, I would mean that U becomes exactly the same as U tilde apart from the dimension. Now it becomes, well, equal apart from maybe some trivial algebraic step. I mean.
In the case when U tilde is non-unitary, it does have otherwise properties, no? Is there not a kind of dissipative structure?
No, unfortunately not. I mean, there will be a dissipative structure. There will be kind of a Krauss map structure somewhere on the way, if I arrive there. But this will be due to this Euler averaging. Yeah, this Euler averaging will give you some sort of dissipative structure. Yeah, but that is
only when it is unitary.
But that's only when you sit at the self-dual point where this guy without averaging is unitary. Unfortunately, no. I mean, it would be great. I mean, okay.
It does preserve what? It does preserve positivity, for example.
Yes. 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 So let me try to. Okay, so now the next step is how to calculate. So now you see, I mean, okay, we performed basically the first step, right? I mean, we formulated this guy in terms of some sort of transfer matrix. Now let's try to, but of course, the non-trivial part is to perform the averaging, to perform the next step. So now I will need some space. So now I will compute this, right? Expectation value of trace of U to T. Trace of U star to T. If you want everything star, whatever. Like this. By star, I mean, again, complex conjugation in computational basis, or complex conjugating the whole term, whatever you like. Now I write it as a 2 copies, right? And then I do expectation value over the set of the fields. And in parallel, I will try to make a picture which will illustrate this calculation. The picture will be then, again, 2 copies. Okay, I'll do this, and then I have another 1, 2, 3, 4, 5. 2, 3, 5. So this will be now denoting trace of U to the T. This will be trace of U to the T star. Another will be field, which will differ from. Now I want to, of course, use this dual transfer matrix. I call this guy dual transfer matrix, U tilde. I want to use this guy to contract in the vertical direction, but I want to do this in parallel for both copies, right? That's why I make this picture like this. So that will be some HL, and so on. And okay. Okay, so now, we use duality formula. And of course, due to cyclicity of the trace, I think due to the symmetry of this, actually this transfer matrix can be written in a symmetric way because it is, I mean, it corresponds to time reversal invariant system, so the order of this product is not important. And now I do again the same trick as I did yesterday in my super simple example. I write this as a trace in the tensor product. So I'll put now these copies together, and I'll write it as a trace. So now it's a trace over the product space, over a space of dimension 2 to the t times 2 to the t. It's 4 to the t. Okay, and right, but now you see, I mean, this becomes a product, right, of such terms. And now I can pull now this averaging inside, and I can do, because this Hj are IID, so which means that I can average an expression which is a product of expression which only depends on single component. I can average as a product of the averages. I can write it as a product of the averages. So this is basically a trace over a product of the averages, where now each average depends just on a single, which averages over a single component of the field. So I can basically, okay, I will do the picture later. First the algebra, then the picture. Okay, so now what we are doing here is we are use the blue color. Now what I denoted now is, this will be now my transfer matrix, which is 4 to the t times 4 to the t, which is this thing, and this thing is the same. See, I mean, what is now remarkable here is that this guy does no longer depend on the index j. So it's the same for any side. So basically this is just a trace over power, I will denote this as double t, power to the L of some transfer matrix, which is defined like this, where t is defined as rotation value over a single component of the field of U dual transfer matrix tensor and then average. So basically it's a unitary, right? The tensor product of two unitaries is a unitary, is an independent product, I mean, of two systems which are both unitary. The point is that they are coupled through the disorder averaging. So the fact that they share the same disorder means that they are coupled. And this coupling makes the whole evolution non-unitary. Actually makes the whole evolution like a noisy evolution. Okay, so now let's continue. So let's now try to basically shape this really as in a form that you will see it looks like a nice map. So so now let's introduce some disorder averaging. Now let's assume that we have a Gaussian disorder. We define an average over function with a Gaussian kernel, which has mean h bar and variance sigma. Okay, and let's try to do that explicitly. I mean, we all know how to do Gaussian integrals, right? So I will do these steps quite quickly, but still I want to write things explicitly. So now what I can do, I can take out the h dependence explicitly here. So first I will write h kick-teasing. I will write it as h dual transfer matrix at some field h. I will factor it in to the case where the field is 0. This is longitudinal field. So if you look at again how it's defined, it has Ising part and a transverse field, but the longitudinal field is in the Ising part, so we can factor it out, which means you can write this as as the whole thing with 0 longitudinal field times from the left, from the right, you multiply by times e to the minus I h times mz, where mz is the total magnetization in z direction. So tau runs from 1 to t, sigma z tau. Okay. So now we have t sides, right? I mean, the model, each copy has t sides, and this is z magnetization in this direction, right? So now, and this is basically the transverse field, right, case. This case is the model with transverse field, with no longitudinal field. So this model can be mapped to free fermions. Yeah? I mean, if one does Wigner-Jordan transformation, this model maps to non-interacting fermions. So basically, it can be exactly treated. It's a free model. Yeah? But the non-trivial part is the longitudinal field which perturbs it. So now, but now we want to spell out the averaging. So we took out these things. Now this is star, and this is now plus IHMZ, right? And now you see we can write this. Obviously, we can take out this. This is now, again, using this elementary algebra, we can take out the field independent part, the free part, and factor it times the expectation value of e to the minus IHMZ tensor e to the plus IHMZ, okay? And then we calculate just this part, and this part is this can again be written as a kind of, as you see maybe already, exponential of the commutator, generator of the commutator, right? I mean, again, you can write this as exponential of mz times identity, and this as exponential of identity times mz. You put it in the common exponential, and you get this, right? But now this is something that's nice. Of course, I lost the field somewhere. This is exponential of a linear expression in the field. This is a Gaussian average, so everything is again a Gaussian integral. And it's a trivial exercise to show that the result is again something which is a Gaussian-like kernel. So it is result of this calculation is e to the minus 1/2 sigma square mz 1 minus 1 mz square. So that expression squared minus I h bar, the average field mz 1 minus 1 mz. Okay, is this clear? I mean, that step. I didn't do that step, but that's an elementary Gaussian integral. So I just put inside this expression for this definition, and I perform the Gaussian integral, right?
The star, was complex conjugate or a division?
Complex conjugate. Yeah. Sorry, I use star for complex conjugate here. Okay, so now we are done. Basically, we have written the. Now I have to stop using that board. I have to go on the other side. So now what we have done is we have written the transfer matrix as a product of the unitary part. Now we can put inside again that piece. Now this piece, of course, these two guys here are commuting. We can again put inside this piece again inside the unitary part, right? That's still unitary, but that's non-unitary, right? See, I mean, that is I times the Hermitian operator. That's a positive real thing times the Hermitian operator. Yeah? So that's actually a nice operator, right? I mean, it's Hermitian, and that's a unitary. But about commuting, you put the unitary part together with the free evolution, and you get H average times a unit vector tensor. Now, star here, stress complex conjugate. If you want, or transpose, is unitary. Okay. Times an operator which I will call the averaging operator. And that averaging is just exponential. Okay, so, and now what we want to, the problem we want to study now is the spectrum of this transfer matrix. We want to establish at the end of the day, actually, our goal is rather modest. I mean, it should be modest at this point. I mean, we want to discuss what happens to this form factor in the large L limit, so in the thermodynamic limit, but at fixed times. So we want to see whether there is ramp, but we don't care if we move Heisenberg time to infinity at this point, right? I mean, maybe later one would want to study also what happens at around Heisenberg time. Then this would not be accessible to our analysis if we want to study the spectrum of this guy. But now let's just study thermodynamic limit. If we study thermodynamic limit, then we basically have to count eigenvalue 1 of this guy, right? I mean, basically eigenvalues on a unit circle. Now, first of all, I mean, there are a couple of observations I will make now here about this. I have only 20 minutes left, so I am probably not able to prove anything here, but this was the main thing I wanted to do, so to express the form factor in terms of this transfer matrix, and then to tell you how to study this transfer matrix. So, I mean, there are a couple of observations which are almost obvious. So now, I mean, I will now write a limit, thermodynamic limit of the spectral form factor. And then basically, that amounts to establishing two things, right? To study this limit amounts to establishing two things. First, count multiplicity of eigenvalue 1 and establishing a gap of the rest of the spectrum from the unit circle. So now we have two goals. Establish a gap. So what happens is that this is a transfer matrix and the spectrum is, well, first of all, I will, as I say, I will write down at least or spell out for you a sequence of almost obvious observations you can make about this. And one of them is that the spectrum is confined to a unit circle. And that's kind of, should be almost obvious, right? Because this map is a product of a unitary times a contractive map. This map obviously has a spectrum which is strictly, not strictly, but within unit circle, right? Basically, this guy, this is an exponential of this map. This map, of course, has a large kernel, yeah? But for everything, so for that, guys which are in the kernel of this map, this guy gives identity. But then there are vectors which are not in the kernel, and for that, this guy shrinks them, right? I mean, this guy is a positive operator, and this is exponential of a minus positive operator, so obviously it has a spectrum within unit disk. Yeah? So now we have a unitary times something which has a spectrum within unit disk. It's obvious almost to recognize that the whole thing has a spectrum within unit disk. So now let me just state a couple of properties. Property one, the first part is eigenvalues of T have at most unit magnitude. and eigenvectors corresponding to unimodular eigenvalues are simultaneous eigenvectors of O sigma and U star of both parts, of both pieces. And that's super simple to see. I mean, I actually wanted to show that, but maybe, okay, at least the first, well, there is the second part to this, saying that for eigenvalues on the unit disk, for unimodular eigenvalues, the geometric and algebraic multiplicity coincide. So basically it tells, I mean, I will not even spell it out. I mean, I will not even write it down because in the lack of time, I just say it in words. So for all eigenvalues on a unit circle, or possible eigenvalues, there could be no non-trivial Jordan block. So that geometric and algebraic multiplicities of each such eigenvalue are coincide. So they are basically, yeah, things is basically stable. Okay, so now, but yeah, probably it's better not to spell out the proof. I mean, it's kind of super elementary, so I think everybody interested can do it or check it in our paper. Actually, before I forget, I mean, I just give you the reference. I mean, this has been developed in the paper together with Bruno, he's here, and our course, graduate student in Ljubljana, and myself, which was published in PRL at the end of last year. So you can check the details of this calculation and the proofs there. So there are a couple of, now I will just try to go a bit quicker through these observations because I'll just try to stress some intuitive points, not so much the formality. So now we have the map. Now I want to write this map as a kind of completely positive map on a density matrix, right? I mean, this map so far is still written in terms of a vectorized picture, if you want. In terms of, this is like a super operator, right? I mean, it acts on two copies, which you could consider as a bra and the cat of a density matrix. And the fact, I mean, what we have now basically is, okay, so what we are studying now is eigenvectors, which are joint eigenvectors of both pieces, because those are of interest for us. So now let me just discuss this. And then the fact that you have eigenvalue 1 of, I mean, that thing has a real spectrum. So the only eigenvalue which is on the unit circle is eigenvalue 1, right? There's a positive real spectrum. So obviously, because it's exponential of something which has a non-negative spectrum. So which means that the fact that this guy has eigenvalue on a unit circle means that this guy has to be an eigenvalue in the kernel of this guy, right? So for any other eigenvector, we know that it is strictly inside the unit disk. So we know that we only have to study this type of eigenvectors, and for any other eigenvector, we know that there is a gap. Which is positive. And all the other guys are here. Okay. Right. But now, as I say, I mean, I will now try to unvectorize this map. So now I can write this vector as a, I mean, this vector is defined in the tensor product of two Hilbert spaces of two T-spins, right? Each of HD is Hilbert space of 2 to the T, the measure of 2 to the T, two T-spins. So now I can write, in general, I can write an element of this space like this, where in some basis, where if this basis is some non-trivial basis, I have to use complex conjugation here, which means complex conjugation with respect to sigma z basis. But if I use sigma z basis, I don't have to care. And then there is a linear map between this guy and a space of operators. So then there's a linear map. This guy is an element of HT, tensor HT, and this guy is a linear map over endomorphisms over HT. So it's an element of that. So then, yeah, right. So you just do the standard thing when you unvectorize or vectorize if you want. And after this operation, you can simply define this as two conditions on the operator A. So now, I mean, this map gives you a one-to-one correspondence between element of this tensor product space and the space of matrices over HT. And now we have just these two conditions are now equivalent to a condition on the matrix A. And of course, the whole map can now be written as a completely positive map over space of density matrices. Okay. So now this guy now maps to a left. This is left multiplication with U, and this is right multiplication with this guy transpose. So this means transpose star means Hermitian conjugate. So it's like conjugation with a unitary is equal to the e to the I phi a. For some real phase, of course, here phi is assumed to be real. This is assumed to be unimodular eigenvalue. And the second constraint is that this guy has to commute with mz. Now there is a second property that allows us to show that these two conditions for any A are equivalent to a slightly more elegant set of conditions. So this is equivalent to saying that this guy commutes with any generator of SU2, global SU2. So M alpha I now define as sigma alpha tau from 1 to t. Alpha is x, y, or z. So this is equivalent, again, to asking that A commutes with any component of the generators and any component of SU2, any mx, my, mz, and it commutes with a simpler unitary, and it essentially commutes, or after conjugation with a simple unitary, which I will now just write as U, gives e to the I phi A, and this unitary is has a nice interpretation. It's basically just the Ising, just the Ising energy, right? But I write it in a way that it will allow you to make some sort of nice interpretation. Okay, so now I just subtract some phase, which is irrelevant. So now what is this? I mean, this is just counting whenever you have a domain wall, right? I mean, whenever two adjacent spins flip in the opposite direction, you count here as minus 2, right? Times pi over 4 is minus pi over 2, so it's basically a factor of I, right? For each domain wall. So basically this is minus 1 to the half number of domain walls. So basically it's a diagonal operator in computational basis, and in computational basis it just checks it's diagonal, but it just gives a number plus or minus 1, because number of domain walls is an even number, right, for periodic arrangement of spins. So this number is always real. Right? This number is, it gives you an I, but it gives you twice in I, so it's always plus or minus 1. So it gives you the number which is just parity of number of domain walls, parity of half number of domain walls. Yeah? So basically, that's a very innocent, I mean, it looks innocent, but it's actually quite deep. I mean, it basically selects a space of A's to a space which dimension which we want, which is 2T. I mean, if you just look at the first condition, of course, there are exponentially many A's which commute with all elements of generators of global SU2. But now we also ask them to phi commute with this domain wall parity operator, and then this selects these guys, confines these guys to a much smaller space. Okay, I mean, is it more or less clear? I mean, I don't know. Have I lost you completely, or? I don't know. So now there are two things which we can immediately see from here. For example, phi cannot be anything, but the fact since u square obviously is identity, we say eigenvalues are just plus or minus 1, which means that phi could only be 0 or pi, right? Because you repeat this twice, and then from here it follows that phi can only be 0 or pi. So eigenvalue can only be plus or minus 1. So nothing can be elsewhere on the unit circle, but just at plus or minus 1. Well, that's very nice, yeah. And moreover, one can show that for now, basically, one has to restrict himself a bit to proceed rigorously. That is, if one constrains himself on to odd values of time, so now another property is for odd values of time, phi needs to be 0. So which means that the only eigenvalue is 1. I mean, this can be shown by studying the case of the free case, the quasi-free case. So it's not so easy to show. But once we have this, then basically, so now let's specify, I mean, now let's just discuss for the moment the odd time case. For the odd time case, we have shown that the only eigenvalue on the unit circle is 1. And now the only thing we need to do is to discuss the space of operators which simultaneously commute with U, with domain wall parity operator, mx, my, and mz. Right? So basically, we need to have the commutant of this set, right? Okay, and now there is basically a theorem which you can show, which says that now basically we are looking for all elements, all linearly independent operators, because this is a linear set, right? I mean, we need the dimension of this set. We need to count multiplicity of eigenvalue 1. So each operator which commutes simultaneously with these 4 guys represent an eigenvector of eigenvalue 1, right? So now we basically have a lower bound immediately. We can figure out immediately what are the 2T eigenvectors or 2Ti operators which commute simultaneously with these 4 guys, right? So, so let's call this M. The theorem, any element of M is of the form A, this is some tau goes from 0 to t minus 1, n either 0 or 1, some coefficients, some complex coefficients, tau n times pi to tau r to n, where pi is a translation, periodic translation on a lattice, which can be generated in terms of transpositions, and r is the reflection. Again, both are written in terms of transpositions. I will write them. I mean, so these are particular representations of translations and reflections over Hilbert space of T-spins, so to the dimensional space. Okay, so now this P, I can write this P explicitly. Pjk is 1/2 identity plus sigma j, sigma k, right? So that's a transposition. So now basically what we have shown that its A can be represented in terms of generators of the basically dihedral group. Again, a symmetry group of polygon with T vertices. But now represented specifically in the Hilbert space of T-spins. So in a many-body space. So it's not clear a priori that all these generators are linearly independent operators. Actually, it happens that all these guys are linearly independent only for T larger than 5. For T5, actually, there is one relation within this representation which is satisfied, one non-trivial relation, so the space has one dimension less. So it's kind of tricky. I mean, but now it becomes pure algebra, so I think I don't want to torture you with this. So I just, yeah, so did I tell the theorem yet? Not yet? Yeah, I did. Okay, so this any element of this commutant set is given in terms of linear combination of 2T elements. So it has dimension. Equal to T. Now, I mean, this is of course for odd T. I assume that the time is odd. For even times, situation seems to be mathematically much more tricky. So we have not been able to get any rigorous result for even times. So basically, the result, if I just conclude, and of course, I mean, I don't know, I mean, yeah, I think I should better allow for some questions, so I don't want to go much over. So I wanted to give you some idea of how to prove that. Basically, again, is, I mean, you go to the Fourier space, and there you try to show that the Fourier components are irreducible. This algebra is irreducible in each Fourier component, and then you get T Fourier components in time space. But then there is another factor of 2, and so on. So, but again, I mean, I guess it would be anyway too formal to be comprehensible in a few minutes. So I prefer to make some comments for the end. So basically, the statement now is that for odd times, K of T is 2T minus 1 for T less or equal to 5, and 2T for T larger or equal to 7. Yeah. And then for even T, for even times, we only have a conjecture. For even times, we have a conjecture. Sorry, this is L to infinity, thermodynamic limit. Well, conjecture is that this is 2T plus 1 for T larger than or equal to 12. So this 1 comes from another eigenvector, from another element, from another operator which simultaneously commutes with all these guys, which is not of this form, which you can figure out. It's a projector. It's a pure projector of this form. And it's related to the oddness of this representation, to the evenness of the dimension of, I mean, number of elements, number of spins. So it will be easily explained. Of course, this one can be explained, but it cannot be proven that there are no other guys, right? I mean, you have not found any other by just inspecting empirically or numerically this problem for times up to 17, but that's not too much. I mean, of course, we have to stop there because the problem is exponentially scaling. The computational cost is exponentially scaling with T, so we have to stop there. So I mean, this kind of, to prove that is still kind of in the air. Anyway, so I think, but it's kind of nice to have at least, you know, for half times to have strictly the kind of prove that one specific model satisfies random matrix spectral fluctuations, at least spectral form factor. Yeah. Now, of course, I have not commented now. Of course, this model is still, I mean, this model still has a disorder, right? So this model has disorder. So, but you see, I mean, this is true for any disorder strength, which is positive, right? So you can put at the end of, if you want, you can put at the end of calculation disorder strength going from 0 to 0 from above. Yeah. So basically, you can take a limit of a clean model, and again, you get a random matrix result. Of course, this has to be done in the end because otherwise, model has additional symmetries. It's translation invariant. So, okay. So now, basically, this is the main point of the second part. I had also the fourth part on my menu yesterday, but it's. I mean, probably I leave it to the question or discussion part. Now, one can ask, of course, this was a very specific model, so one can ask, what is the general class of models for which this analysis can be performed? And these are fine-tuned models, but the question is it really so much fine-tuned? And I will just give you sort of a 2-minute introduction into this general kind of classification of this type of self-dual, dual unitary models. So basically, you can write all these models as, you know, in a these days very popular kind of setting, which is this local quantum circuits. So you can think of these quantum spins, 1, 2, 3 to L quantum spins, as basically being propagated in terms of a quantum circuit simulator, right? And for example, this Kick-Teasing model can be written exactly in terms of quantum circuit for some specific unitary U. So now let's just say we have some unitary U here. These unitaries could be different for any space point, time point, but now this is I'm sorry, now time is going vertically here, as usual in this literature, and space is now horizontal. Right? And now basically you can ask, and you see, I mean, the main trick that we have used, I mean, I'm just using a few words now and then I stop. The main trick we have used now was the fact that we were able to flip space and time. So basically the idea was that if you flip space and time, the propagator still remains unitary. Now you see, I mean, the full Floquet operator is these two layers, right, of the circuit. And that's the whole unitary operator, right? But now you can also do this and propagate in space. And now you ask that this to be unitary, and this with the U tilde. And for that to be unitary, you need to study just the elementary gate, which maps two states ij into states kl. And you want to define U tilde, which is basically the same map, but where it takes as in states I and k, and takes out states j and l. So basically, you just take a reshuffling. I mean, people who do quantum information, they know this kind of procedures. You just do reshuffling. This is a map which acts on 4 spaces, on 4 particles. 2 is in, 2 is out. And then you just reshuffle indices so that the other 2 is in and the other 2 is out. And what you want is that both U and U tilde are unitary. And this gives you automatically that the whole circuit in space direction is given by the unitary propagator. And this is what we call dual unitary. And the self-dual Keiji is just a special case of that. So and it turns out that you can classify this for qubits. For qubits it's much harder, but this type of models, we believe, I mean, okay, this proof of random matrix spectral form factor has to be redone in general, but we believe that for a class of models which are chaotic, again, these models are, I mean, studying this model is kind of very rewarding because you can find examples which are integrable, chaotic, mixing if you want, dynamically mixing because correlation functions decay exponentially or they don't decay. They are not even, there are examples which are not ergodic but not integrable and so on. So you can find a full ergodic hierarchy within this class of models, yeah? And fully chaotic and mixing ones, I mean the ergodic and mixing ones, they will satisfy random matrix spectral form factor. And it's still an open question how to prove to fill out the details because, you know, algebraic structure is not as elegant as for Keiji model, but we believe that this provides a general setup. So as a reference, I just want to point out, I mean, there was a paper published yesterday in PRL, again, by the same authors, where we kind of discussed this topic. So it's really fresh. Okay, with this, I would like to thank for your attention and start.
Questions or comments?
This analysis, whatever the analysis, is it holds only for self-dual or dual?
Is what? This analysis, you mean the spectral form factor? It's only for self-dual, yes.
Only for self-dual.
Yes.
So, yeah.
This
what is the statement for the dual? If you just consider the dual.
Dual unitary?
Yeah.
The statement is that we believe that it should be doable, but it's a bit trickier, yeah? Because, as you understand probably, yeah?
Yeah. That's where.
I believe it should be done, doable, yeah, but I guess mathematics should be more hard, yeah? I mean, it's probably harder. I mean, it's not, we are not able to express the problem in as elegant algebraic way as we did for Keiji. So Keiji is especially nice. It's like a harmonic oscillator of these chaotic systems, yeah. But
what other models, other than this model, exhibit this self-dual characteristics? Do you?
Well, I mean, there are many models. I mean, I mean self-dual character.
Self-dual.
Yeah. I mean, we don't know any other non-trivial example. I mean, the Keiji model is a family of models, but I mean, family in the sense that you can put disorder and still be self-dual, but it's one model. So, no, I mean, I'm not aware of other examples. I mean, you probably, you mentioned you know, in higher.
Yeah, but not we are not able to get the exact model, but we were able to generate these dual unitaries instead of models. So that's
for that dual unitaries, we have used so far for other purpose, to compute correlation functions. Yeah, the idea here was to compute exactly dynamical correlation functions for arbitrary local observable. Maybe to study transport at the end. Yeah, that is their motivation. But not to study spectral form factor seems to be trickier.
That's what.
It's another question.
Yeah. Thank you.
Yes, for dual unitary also. Yeah.
Just at some point you said that any eigenvalue of unit modulus has to correspond to an eigenvector simultaneously of u tilde cross u tilde star and the MT, right? Is it correct that this was the point at which we started using that u tilde is unitary?
Yes. Right. Yes.
So if not,
yes, everything before that is still true for non-unitary u tilde, but we are not able to say much beyond that. Yeah. Right. Then we can start playing with numerics. And that's actually a very interesting point because then, we could study, because, for example, in this particular point, there is no localization, right? We've shown that there is always ergodicity, yeah? But now we want to go away because there is claims that Floquet systems can localize, yeah? So now let's go beyond, and then we have to establish some statements about the spectrum. And it's clear now what would be the signature of localization, would be that at least one of the eigenvalues should approach 2, because then the thing would be 2 to the L, and then it would be Poisson, yeah? And, right, so then the question is how to study that, yeah? So then, well, we are trying now some perturbative approaches, but it's hard.
So looking at your picture about the circuits, I mean, could you do also the diagonal transfer matrix maybe? I mean, like in the 6-vertex model, I mean, you would sort of,
yeah.
Is that
actually, yes,
the advantage, or, is also helpful? I mean, you sort of emphasize it's very important to, first, do the spatial transfer matrix, so to speak, right? I mean, you could also do.
Yeah, sure. Yeah.
Any advantage or
not that I know
really?
of so far?
Oh, okay.
I mean, in some different context, I was playing with diagonal transfer matrix. I mean, but maybe in the talk I give after lunch, I mean, I discuss this classical cellular automata. I mean, there you can write diagonal transfer matrices, and it would be corresponding to some light cone steady states or something. Yeah. You can do that, you can find results, but I don't learn so much from them.
So in your first model, you have this soulless time, which was log L, whereas here, as far as I can see, it doesn't exist at all. You have random matrix theory.
Is one.
Is one. Okay, yes. So what is the understanding of, so first of all, what's the essential difference between the models that explain this? And another question, and what is the reason, is there any physical understanding of this log L? Because we know, of course, what soulless time is in models when there are some conserved quantities, so that you need some diffuse through the system, but it's apparently not the case in your models. So what is the reason for log L there, and
well, I mean, what is the reason? Yeah, I don't understand really the reason for log L. I mean, I don't know if someone understands. But here, even, right, I agree this looks a bit strange. I mean, first of all, there is no conserved quantity, so there is no bound like L square from diffusion or something. But, and the fact that it's one is a kind of strange because we have locally interacting system, right? And then it thermalizes at time 1 in some sense. I mean, but that's not proper thermalization because it is not formulated in terms of local observers. Local observers still need time of L, right? And still need to propagate across the system. But this is a very non-local thing, right? It's a spectral correlation. So it can become random matrix in time 1. I mean, it's puzzling. Yeah, I agree. I mean, one would like to have interpretation, but so far it just so happens, yeah. Of course, if you perturb the model, then immediately you shoot off. I mean, Taoist time becomes of the order of L, maybe. I mean, it's not clear. I mean, it's very hard to get convincing numerics, but obviously for finite L, you have Taoist time, which is of the order of few 10, let's say, from numerics. So, I mean, for, let's say, few 10 steps, then things deviate from random matrix and then they go along the random matrix. I think, I mean, to me, the most exciting study here is now to perturb, to shake these models. I mean, I didn't say that, but now I can probably say that. I mean, see, I mean, we all like to perturb integrable systems. We all like to perturb free theories, and we know that there are problems with perturbation theory. Now, if you look at mathematics, people have perturbed chaotic systems, strongly chaotic systems, and sometimes they have proven theorems that these are stable, that are structurally stable. So now it would be nice if this model would be structurally stable. Of course, it's wishful thinking at this point. But suppose it is. then you would be able to show that there is convergent expansion around this, and then there is a ball of models which have behave like this. That would be great. I mean, this is my dream, but so far I have nothing to say.
Okay. Guys, other questions or comments? If not, let's thank speaker again. Now coffee break.